Let's start this problem again on friction. It says that a block of mass m, mass of the block is m, kept on a rough horizontal plane. Rough horizontal plane means there will be some friction. The coefficient of friction is given. The block is pulled by applying a force to it. What is the minimum force required to pull the block and in which direction? Let's draw the diagram for this. It says the block is kept on a rough plane. So this is a rough plane, let's say, and this is the block of, let's say, this block is of mass m, mass capital. Now it is pulled by a horizontal force. Again, let us find out the various forces acting on this. There is a downward gravitational force, capital Mg. Of course, there is a upward reaction, R. Now, this reaction R, normally we take equal to Mg, but here it is not so because there is a additional force which pulls the body. And also it talks about an angle. So let us say the body is pulled at an angle, say this angle is theta, and the body is pulled by the force F. So there is a vertical component of F, there is a horizontal component of F, which is equal to this horizontal component of F is F theta, and vertical component of F is F sine theta. In addition, there is a frictional force, Fs. This is equal to mu into the reaction R. Now, let's first consider the vertical forces. Consider the vertical forces. When we consider the vertical forces, we find vertically upward is F sine theta and reaction R. So reaction R plus F sine theta will be equal to vertical downward force mg. Will be equal to downward force mg. From here, that the reaction R is equal to mg minus F sine theta. As I was telling at the beginning, reaction R here is not exactly equal to mg. It is mg minus F sine theta. And now let's take the horizontal forces. Horizontal forces. The trick is you have to only identify the forces in rectangular directions, vertical and horizontal. If you can identify all the forces, you can always solve the problem. Horizontal forces is F cos theta equal to mu R. Cos theta is equal to mu R. Say this is equation 2. Say this is equation 2 and this is equation 1. So from equation 2, from 2 we get f cos theta is equal to mu r. R is given as capital Mg minus f sin theta. So it is mu Mg minus mu f sin theta. From here we get f theta plus mu f theta is equal to mu m. What do we get? From here, what we get is f is equal to mu mg divided by cos theta plus mu sin theta. Sin theta. Now, if you look at this finding, the force required is cos theta by mu sin theta. That means force required depends upon theta. And there is no directly relation. It increases as sin theta or decreases as cos theta because both sin and cos are there. So anyway, it depends upon theta. That means the amount of force that will be needed here, it depends upon what angle you are making, right? Now, they want us to find out what minimum force is needed. So we want minimum. Now, if you remember your mathematics classes, how to find out the minimums. We can write F theta plus mu and theta is when cos theta plus mu sin theta is maximum. Obvious, when cos theta is plus mu sin theta is maximum, then F will be. Then how do you find out the maximum? At what angle? So question is, it becomes maximum at what angle? Theta. That is the question. If you want to find out that at what angle theta, cos theta plus mu sin theta will be maximum, we have to find out the theta derivative or d theta of cos theta plus mu sin theta and equate that to 0. This comes from your mathematics laws of the differential maxima minima chapter. From here, we get d theta of cos theta is minus sin theta plus mu, and d theta of sin theta is cos theta equal to 0. From here we find, if we take sin theta on the right hand side, sin theta is equal to mu. From here, if we divide both sides by cos theta, we find tan theta is equal to mu, which makes the theta is equal to tan inverse mu. This is the angle, tan inverse mu. This is the angle. At that particular angle, if you apply the force, then the required force will be minimum. The question also asked in which direction you have given the direction. At an angle, tan inverse mu with the horizontal. And also they asked what minimum amount of force is required. It will not be difficult now. You have to only find out F by putting the value of theta. Theta is tan inverse mu. So then F is equal to, from this equation, mu mg divided by cos theta plus mu sin theta. We have to bring in tan theta somewhere. So we divide everything by cos theta. Mu mg divided by cos theta, that multiplied by, if we that multiplied by 1 plus mu tan theta. This is equal to mg divided by cos theta, and tan theta is equal to mu. So if tan theta is equal to mu, this is 1 plus mu whole square. 1 plus mu square. This is 1 plus mu square, right? Now, we do a little bit of trigonometry. We find out cos theta in terms of tan theta. That is not difficult because we know that sec squared theta is equal to 1 plus tan squared theta. From here, we get 1 by cos squared theta is equal to 1 plus mu square. Plus mu square because tan theta is equal to mu. 1 plus mu square. So, therefore, we get 1 upon cos theta under root 1 plus mu square. That is so. Then what is the value of F min? Therefore, F min is mu mg 1 upon cos theta is under root 1 plus mu square multiplied by under root 1 plus mu square, and that multiplied by another 1 upon 1 plus mu square. This becomes mu mg divided by plus mu square. So this is the value of F min, and this is the angle at which you have to apply the force so that the body starts moving. We go to the next question. In the next question, it says that the friction coefficient between the floor and the board shown here is mu. That means the friction coefficient here, the floor and the board is mu. Find the maximum force that the man can exert. So man is exerting a force here, which resulting into an upward tension T. What is the maximum tension so that the board does not slip? Understand the problem. Say the man keeps on pulling it hard and hard. If he pulls it very hard, then actually tension will be so high, the man will start hanging with the rope, and then the body will slip. Then the small board will slip. So question is, how much maximum tension or force the man can apply? So here, let us first take the free body diagram of the small body. Let us take the free body diagram of small. A free body diagram of small m. Then what we have, There is a, this is the board of mass small m, and there is a reaction, there is a reaction given by the person, or rather what I do that will be easier for you to understand. Let's take the free body diagram of, uh, the man first. Let's take the, consider free body diagram, free body diagram of the, free body diagram of the man. Then what happens? This is the, this is the man, and this is the man, and this is the board below him. This is the board below him. This is the man. Now, here there is a upward tension T. Actually, if the man pulls the rope by T, there is equivalent upward tension T. There is a mass of the man. There is a mass of the man. Mass of the man is capital M G. The mass is given capital M. And there is a, of course, there is a reaction R, the reaction which is applied by the small board, supplied by the small. In this case, the downward force is capital Mg. So obviously, capital Mg will be equal to the two upward forces R plus T. This is one equation. This is easier to understand. Then we take the free body diagram. We take free body diagram of the board only. The board only. Then this is the board of mass M. If the board applies a reaction capital R on the man, the man applies a reaction R downward on the board. And there is a floor below. Let us say this floor applies a reaction smaller. Applies a reaction smaller. And in that case, what we find, and of course, this body is M, so this has a downward force, small m g. From here, we find upward force smaller minus, or rather, you can find capital R plus mg equal to small r. So you can find capital R mg r. Right? This is one equation. This is one equation. This is another equation. And also we know the frictional force. There is a tension T in this direction. So there will be frictional force in this direction. This frictional force, this frictional force Fs, frictional force Fs is equal to mu multiplied by the reaction force small r, and mu multiplied by this reaction force small r, right? Now let us take the equations one by one, right? Now this and this, there is a tension T. Of course, this frictional force will be equal to T. So we can write it this way. T equal to Fs, the only two horizontal forces, and Fs equal to mu1. Let us call this is equation 3. Let's call this equation 3. And let us call this equation 1, and let's call this equation 2. Right? Then from equation 3, from equation 3, what do we get? T is equal to mu r. T is equal to, now the value of small r is available here from equation 2, which is capital R plus mg equal to mu capital R plus is equal to mu. Value of capital R is available here. Capital R is equal to mg minus t. So this is equal to, this is equal to mg small mg plus capital R is mg capital Mg minus tension T. Now, what we get? T is equal to mu plus mu capital Mg minus mu T. That makes T multiplied by 1 plus mu. If you take mu T to the left hand side, is equal to, you take mu G common, you have small m plus capital M. From here, we get tension T is equal to mu G multiplied by M plus M divided by 1 plus mu. So, this is the maximum tension this man can apply on the rope. If he applies on the rope more than this, the tension will tend to lift the man up, and the same tension here will tend to slip the board down under his feet. So these are the two problems. Next we shall see more problems on friction.